Hello everybody, this is lecture 4 and it is chapter 6 in the textbook, control charts for variables. And we are going to have chapter 7, it is control charts for attributes. There is a clear distinction between the control charts for variables and control charts for attributes because there is a difference between the data types in both cases. In variables, we are talking about the continuous data. In attributes, we are talking about non-continuous, the discrete data. That's why we are going to use different kinds of control charts for each case. So we separate the chapters for variables and attributes. Okay, let's continue for control charts for variables first. We use control charts, and as you remember from the last lecture, the control charts are one of the tools we use in statistical process controls, right? And we use statistical process controls for reduction variability, so we can increase the quality, right? We can improve the quality. And we are using the control charts for the same purpose, reduce the variability. For this, in control charts, we are going to maintain control over the mean and the variability aspects of the quality characteristics of a product. So what does it mean, the control over mean and variability? Let's check these figures. In the first figure, we have nominal values for the mean and the variability. Okay, this is the standard deviation and this is the mean value. Let's call them as nominal values. We have also specification limits, and outside of this specification limits, we have non-conforming product. Okay, so let's check the middle figure here. The mean is shifted a new value, right? So we could not, control the mean. So the mean is shifted. We couldn't control it. So if the mean is shifted, we are gonna have much more non-conforming product. So if we could not control the variability, we will have much more non-conforming product. That's why we need to control the mean and the variability. For mean aspect, we use the average control chart, the X-bar chart, let's call it in this way. For variability, we use R range and S the standard deviation control charts. We use them separately for each quality characteristics. But if the quality characteristics are closely related to each other, we need to use different modification tools, and you can find them in the chapter 12 in the textbook. By the way, in this course, we are talking about the reduction of variability. So what is the reduction of variability? So what do we mean by the reduction of variability? Reduction in variability. So this is the reduction of variability, okay? Let's check the first figure here, the drawn figure. We have mean. It can change actually. This is just a quality characteristics. And we have specification limits K. It can be 1, 2, 3, 4, 5. Doesn't matter. We have specification limits. And when we reduce the variability, actually we do not stretch the specification limits. So we do not trying to narrow them or extend them up, okay? We are using them as same, but we are increasing the probability to products will fall between specification limits. We are trying to increase the probability we are going to have much more product on this region. And let's construct our control charts for X-bar control chart and R control chart. And suppose that a quality characteristics is normal distributed. In this case, the X is here, the quality characteristics, okay? And X is normal distributed with the mean mu and the standard deviation sigma. And we know the mean and the standard deviation value. Let's assume that we both the population mean and the population standard deviation. And when we take some samples from the X, from the quality characteristics, and when we calculate the average of this sample, it will be the X bar. Okay, these are the samples we have, and this is the sample average. This X bar, the sample average, will be again normally distributed with the mean, mu, and the standard deviation will be the standard deviation over sigma, the standard deviation over square root of n. The sample standard deviation change because of the variance formula we have. Just pause the video here and try to remember the variance formula from the statistics course. But the mean does not change because of the expectation formula. And just focus on the constant term, okay? Change the variance formula, right? Just check the formulations here. Sample standard deviation is sigma over square root of n, all right? And we have a probability that the sample mean will fall between on those limits, okay? And this probability is 1 minus alpha. This is the 1 minus alpha. And alpha is the summation of shaded region here. This is the alpha. Alpha is the probability that the sample mean will fall outside of these limits. This is the alpha. This is the probability we have falling outside of these limits. And those limits comes from the normal distribution, okay? We can find them in normal distribution. We can use them because of normal distribution. And you can check here. And you can also remember those formulations. How do we come up with these limits? Because of these formulations, because of the relation between the standard normal distribution and the normal distribution. Just check this out, guys, okay? So let's continue. So if we do not know the mean and standard deviation, the mu, and the sigma, we can estimate them. To estimate them, we are going to use the averages, and we are going to take some samples from the random variable we have here. This is the quality characteristics actually. Let's say that we can take some samples, 20 to 25 samples, and each sample must have like 4 to 6 observations, measurements, okay? So we are going to take the average of them, the average of the sample averages, and it can be calculated by this way. It's just an average formulation, right? So also to construct control charts of X-bar control chart, we also need to know standard deviation, right? Because of these limits, we need to know what is the standard deviation. But we do not know this, so we need to estimate it. To estimate standard deviation, we can use two things. One is the range, the other one is the standard deviation, the usual standard deviation. But in this case, first we do not use the usual standard deviation. We are going to estimate the standard deviation by the range values. And what is range? And range of a sample can be calculated by the maximum observation we have in the sample minus the minimum observation we have in the sample. And this is the range of a sample. And this kind of a measurement for variables, right? Because we are taking the maximum and minimum values of observation and we are subtracting them. This is a measurement for variability, and we are going to use these range values to estimate the standard deviation we have, right? And this is the average of range values. Range 1 is the first sample range, and it goes to the mth sample. We have m sample. We are dividing this summation to m, so we are calculating the average of range value. We are going to use this value to construct the X-bar control chart. In this slide, just right now, for a few minutes, forget this part. Just focus on this word. To estimate standard deviation, we are going to use a relative range formulation. Okay, and the relative range is the W. Let's call it as W. And W is equal to, relative range is equal to range over standard deviation. We are going to use this formulation to estimate the standard deviation we have. The mean of W is D2, and D2 is a value depending on the sample sizes, and it is the mean value of the relative range. Okay, this is just the statistics, and we are using these statistics to estimate the standard deviation. But if you are curious, interested in this topic, you can check the chapter 4 of the textbook, and you can see what is the relative range and why are we using this, etc. Okay, you can find the D2 values in the appendix in textbook. This is the mean of W, and we also have a standard deviation of W, and it is D3. Okay, it is also tabulated in the textbook. You can find them. All right, and just memorize this here right now for a few minutes. The mean of W is D2, and the standard deviation of W is D3. Let's continue. And by this formulation, the estimation of standard deviation is average of ranges over D2. This is the average of D2, the average of W, right? The relative range. And this is the average of range values. And the expectation of the standard deviation will be this, okay? Average of range over D2. And we are going to use this to find the control limits of the X-bar control chart. And we use central line in the X-bar control chart as the X double bar, and it is the grand average, right? This is the grand average, X double bar. We use this as central line in the X-bar control chart. And in upper control limit, we need to find this term, right? This is the central line. We are estimating mean by the X double bar, the grand average. The grand average plus Z alpha over 2 sigma over square root of n. This is the sample standard deviation. This is Z alpha over 2. We see here, right? And in industry, it is very common to use 3 for Z alpha over 2, okay? We are using 3 for the Z alpha over 2. We are selecting it, okay? It can be 3, 4, 5, 2. It's up to us, but it's commonly used in industry as 3. Okay, this is 3 in our case. We have sigma over square root of n again. But we are estimating sigma, the standard deviation, by this formulation, average of range over D2, and it is written here. And it will become, finally, X double bar, the grand average, plus capital A to the average of range, okay? The A2 is here, the 3 over D2 square root of n. That's it. And you can find the A2 values in the appendix in the textbook, okay? They are tabulated. And A2 values, just be careful here. We said we can use different, Z levels. In industry, we said the 3 is a common approach, the common, value for use, but it can be different. But A2 here, it is also tabulated in the book. It is based on the 3, okay? Just be careful about it. If you are using the A2, you accept automatically you are using the 3 sigma limits, all right? And this was for upper control limit, but lower control limit, just the sign of the second term just changes, all right? It is the same for the rest of the part. So let's continue. Let's go back to the original formulation. So this is the control limits for the X-bar control chart, okay? And we proved how can we come up with this A2 values. They are tabulated as an appendix in the textbook. So we need to also we need to control the variability, right? For this purpose, we use R, the range control chart, and S, standard deviation control chart. Let's look at the R control charts first. Again, we are using the relative range formulation, and we are trying to estimate the standard deviation of R by this relative range formulation, and we said the standard deviation of W is D3, and we estimate the standard deviation by the range, average of range over D2. We are gonna number from here, and the standard deviation of range, the estimation of the standard deviation of range will be the D3 multiplies with range, average range over D2, and we are gonna use the average range in the R chart, R control chart as end line in the upper control limit. We need to find the limit term here, and in the industry it is commonly used as 3 here again, and we estimate the standard deviation of range by this formulation. It becomes just that, okay? And by a little manipulation, we can come up a shorter version of the formulation, and we can use the D4, the capital D4, and D3 for the lower and upper control limits. They are just the sign changes, okay? And also this, capital D3 and D4, except 3, if you are gonna use different sigma levels, you don't use the capital D3 and capital D4. You use just D3 and D2, and they are just changes up to the sample sizes. Do not use capital ones, all right? Because they accept automatically the 3 sigma limits, okay? And this is the shorter version of the R control chart limits, all right? These values are tabulated in an appendix in the textbook. All right, so here we have constructed the X bar and the R control charts. X bar control charts for the controlling the mean, and R chart is the controlling the variability. All right. So how are we gonna use these formulations, these control chart formulations? First, we are gonna need to find the control limits, okay? I need to find the central line, the control limits. And this is the phase 1 of the control charts using, okay? In this phase, we are gonna find the trial control limits, and they can be found by an iterative approach. We are gonna take, firstly, a certain number of subgroups. Actually, they are samples, and each sample will have a size of n between 3 and 5, and the number of samples can be 20 to 25 samples. First, we are going to calculate the the central line and upper control limits, right? And it is both valid for the both charts. All right, we are going to calculate them. Then we are going to try to find the assignable causes if we see any out of control points. If we see out of control points, or if we see non-random patterns, we are going to look for assignable causes first. If we find these assignable causes, we are going to eliminate the causes. Then we are going to discard these points from the calculations. Then we are going to revise our trial control limits again, okay? And we are going to continue this procedure until we do not have any out of control points. So we are trying to resolve all the assignable causes we have. And then later, if we do not have any out of control limits, we are gonna accept these trial control limits for use in phase 2 application. Okay? If we do not find any assignable causes, even if we have out of control points, we have two options. One, we are going to eliminate these out of control points. Likewise, we have found an assignable causes, even if we couldn't, and we are going to discard this point, and then we are going to revise our limits because this, out of control limits may be caused by a randomness, because there is a probability for that, and you are going to remember, average run length false alarm thing, in the last lecture we had previous week. Okay, so the second approach, the second option can be, we are going to retain this point, and we are going to consider the limits appropriate for control. So we are not going to discard the point. We are going to count this point in the calculation as well. If there are many out of control points, they should be examined for patterns that may identify underlying process problems. So maybe we have different kinds of problems, but we do not see them. So, and if we see lots of out of control points, we should also must examine the patterns we see in the X bar and R control charts, the trial control limits. Okay. There's an example here. You can, read the details of the example, but I'm not going to talk about the details of the, introduction of the example. Actually, you can check that. You can read them in the textbook. So there is a process. It is called hard bake process, and we have a quality characteristics. It is the flow width. Okay, this is the quality characteristics we have, and we are gonna construct the X bar control chart and R control chart for this process. So we have 25 samples, and each sample has 5 observations on the flow width. Okay, we are measuring this flow width thing, and these are the measurements we have. Okay, we have 25 samples, and each sample has 5 observations. And here we calculate the grand average of the observations and the average of ranges. Okay, ranges, what was the range? A range of sample is the maximum value we have. Let's check. The maximum value we have here, 1.69, and we are going to extract this 1.32 value. This is the minimum observation we have for the sample, first sample. So this is the range value, 1.69 something minus 1.32 something. Okay, this is the range value for the first sample, and we are going to take the average of over all the samples we have, and we are going to take the average of all the samples we have. And those will be the central limits, central line for the X bar control chart and the range control chart, right? This is the average of range, and we have a sample size of n, so we are using the D3 and D4, and we are using the 3 sigma levels, so we can use the capital D for D values here, and n is the 5, and you can find the values in the appendix. And these are the control limits for the X bar chart. Okay, A2 values can be found in an appendix in the textbook. We have calculated the X bar control chart and the R control chart limits and the central line of both control charts. And we can draw the observations, the samples in the charts we have. This is the X bar control chart, and this is the range control chart. These are the samples we have, these values for the X bar control chart. These are the samples, and for the range control chart, R control chart, these are the samples we have. When we plot them in the figure, in the graph, we see that there is no out of control point. on both control charts, so we can conclude that the process is under control, is statistically in control. Okay, so there is also another utility of using control charts. So we can estimate the process capability by the information given in the control charts. So what is the process capability? Process capability is like the measuring the process performance. So this is a simple formulation of process capability. It is in the numerator side, it is upper specification limits minus lower specification limits over 6 sigma. But this 6 sigma thing is not like a constant thing in the process capability ratio. We use 6 sigma because it's commonly used in industry, okay? And it also comes from the natural tolerance limits we have. And this natural tolerance limits in industry taken as in the upper side 3 and in the lower side 3 commonly. That's why we are using the 6 sigma here. And this is just a example figure for the natural tolerance limits and the specification limits we have. This is the mean, for example, mu, and the natural tolerance limit will be away from the mean by 3 sigma in the lower and upper side. So we said we are going to estimate process capability because here in the true process capability we use the true standard deviation value, but mostly we do not know the true standard deviation value, but we can estimate the standard deviation by our formula, right? What is our formula? This is our formula. It comes from the relative range formulation. We can estimate the standard deviation, and this calculation is just the example of hard-baked process example, okay? And we can estimate the process capability ratio by using the standard deviation estimation we have. And in this example, it is 1.19. Okay, it's the process capability estimation. And do not worry about the process capability ratio and other formulation right now, because in chapter 8 we are gonna see those topics deeply. Just try to understand the thing, but do not worry about it, okay? So the main idea here, main notion here, we can use control chart calculations for estimation of the process capability. This is the thing we are trying to give you, all right? So the specification limits for the hard-baked process is given by the designer, and it is between 1 on the lower specification limits and it is 2 on the upper specification. If these are the specification limits, we can calculate how many non-conforming products we are expecting from the process we have. So we have a probability for this. The probability, the product. So we are going to convert this data, this values to the standard normal values, because X is normal distributed, so we can use this transformation to find the standard normal value, X minus the mean, and mean, we calculate the mean by the grand average, right? It's the grand average we use for the export chart, right? It's the grand average. It's an estimation for the mu, we can use it. This is the best estimator we have, the grand average. So we use it instead of mean. And for the standard deviation, we use this formulation, right? We use this formulation for the hard-baked process. And when we convert them into standard normal random variable, we can use the Z table. And finally, we calculate that the in per million product, we are gonna have 350 non-conforming parts. And this is estimated by using the estimation of standard deviation we have. Okay, and we used the control chart value to estimate this value. Okay, for the control, not the control, sorry, for process quality ratio also we used estimation of standard deviation. You see here. Also there is another formulation thing here, and this gives the percentage of the specification band that the process uses up. So process will use up a portion of specification limits, and when we calculate this percentage, it will give us some insights about the process performance. Okay, so this is the formulation we have. So for example, in the hard bake process, this is 83%. So that's the process uses up about the 84% of the specification band. So let's say this is the lower specification. This is the lower natural tolerance limit. This is the upper natural tolerance limit. This is the upper specification limit. And if this is the one, and this is 0.84, it is something like that. Okay, so it's a good sign. Okay, so why it is good sign? We can check on these figures. For example, when the process quality is bigger than 1, the specification limit will exceed the natural tolerance limits. So we expect that by this case, we are not going to encounter so much non-conforming products. But for example, in this case, specification limits will be inside of the natural tolerance limits on the process. So we expect that we are going to have lots of non-conforming products. Okay. So if they are equal, they are going to be matched up to each other. Okay. But the assumption here is that the mean is here the midpoint of the specification limits, but in reality, this is not the case. The mean will be, must have some shift in it, like we have seen in the, the lectures, for example, the previous lectures. We need to have an assumption around the mean, like 1.5 sigma shift, for example. So one of the solutions to reduce the non-conforming product to lower the sigma here, right? So when we reduce the variability, we are going to have much more process capability, so we are going to increase the process performance when we decrease the variability, right? Because the numerator will be the numerator will be same, but when we reduce it, this deviation will be higher. So we can reduce the variability, then we can reduce the non-conforming product. In order to effectively use of control charts, we need to revise the control limits and the central lines periodically. It can be weekly, monthly, or every 100 samples, every 200 samples, etc. We need to revise them, and we need to adapt the new control limits and the central line. And also for the central line in the expert control chart, we can use the target value, desired value, and this is determined by the designers of the product. We can use this target value as a central line in expert control chart as well, but we can use it in the case of the mean is not easily influenced by the adjustment in the processes. If it's the case, we can use the target value, but otherwise we are not suggested to use it. All right. And also about the R control chart, to tighten the R control chart also will give some benefits on the expert control chart too, because when we reduce the variability in the R control chart, so when we eliminate the assailable causes in the R control chart, we're going to tighten the R control chart. Because of the reduction of variability, will also give some reduction variability in the expert control chart too. All right. So in phase 2, we have talked about the phase 1, the trial control limits. In the phase 2, we use the control chart for monitoring purposes. So we are monitoring the processes, and because we have somehow reliable control limits, and here we do not have as much as assignable causes like in phase 1. All right, and also in this phase, we can use run charts showing individual observations in each sample, and this is called as also a tolerance chart or tire diagram. And these charts can reveal some non-random patterns, so we can eliminate the assignable causes resulted in these non-random patterns. As you remember from the last lecture, even if we do not have any out of control point, it doesn't mean that the process is in control, because there are some patterns we can see, and these patterns, they are not random. Okay, they are non-random. These patterns are non-random, and they also give some signals about the process, that the process is not in control, even if we do not have any out of control. Okay, so detect these patterns, we can use tolerance chart diagram. So for example, in the hard-baked process example, we continue. In phase 2, after setting our control limits and the central line, we took additional 20 samples. So we continue to monitor the process. After finding those calculations, sample averages, ranges, when we plot this sample averages and ranges on the control chart, we have constructed this control limits. In the phase 1, we are just plotting the observations, the sample observations. Right now, we do not calculate the control limits and the central line again. We are just monitoring the phase, because in the phase 2, monitoring the process, and we see that after 38 sample, we have a pattern here. There is a run up here. We have some observations away from the central line, right? Then after some point, after some sample, we have 2 out of control points. All right, so there is a thing here, anomaly here, and after seeing this anomaly, we immediately see some out of control points, and the process is no control anymore. Okay, so there are some assignable causes we need to eliminate. Okay, but in the R control chart, there is no out of control point, so we need to handle the control charts separately. Even if we do not have any out of control point R chart, we have in X bar chart, so we need to look for the assignable causes and then eliminate them to make our process in control again. Because it seems that there is anomaly starts from this sample, but the detection of the out of control points take like 5 or 6 samples. So prevent this, we can use sensitizing rules. We have mentioned in the chapter 5, the lecture 3. Okay, you can check the lecture 3 right now. We have some sensitizing rules to detect shifts more easily and previously, in advance. But we need to be careful about to use these sensitizing rules, because in this case, if we use sensitizing rules, we are gonna have lots of false alarms, and we have talked about this problem in lecture 3. Please check it. There is another suggestion to detect these anomalies beforehand, we can use the individual observations, individual measurements by using tolerance diagram. It's also called as tire chart in Minitab, and in Minitab it's a statistical software. In Minitab output we have, for example, in this example again, this is the same example. The box plot shows the observations spreading, the spreading of observation in each sample. Here, for example, we can see an anomaly here, right? This is like a random pattern here, but this is not random pattern. And in tier chart in Minitab, we have seen that the mean is shifted, upward. Okay, the original mean was this, and the mean is shifted after a while. Okay, so even if we have the out of control points after 43, 43rd or 44th sample, we can also say that the process is no longer controlled after 38 sample, even if there is no out of control point here, but there is a anomaly here, so we can conclude that the process is going out of control after 38 sample or something. Okay, so this box plot gives a sense of individual measurements, so we can detect these anomalies beforehand if we also use tolerance diagram. It's a suggestion. Okay, you can use this tolerance tier chart also with alongside using X-bar and R control chart. So about the limits we have seen so far, we have seen tolerance limits, control limits, and specification limits up to these points, and there are different things actually. The control limits are derived from the natural process variability, and this is actually the natural tolerance limits of a process. Okay, when we think about the individuals, this is the natural tolerance limit, but when we take the samples from those individuals, actually we are talking about the control limits, okay? And specification limits are determined externally. These are not related to control limits anyhow, okay? They are not related to each other. There is no mathematical relation between them, because specification limits are set by the designers or the process owners. They are the set values, but the control limits we are extracting these control limits by the retrospective data we have. We are analyzing the past data, and we are taking some observations from the process. Then we are calculating the control limits, and actually we are revising them, we are changing them iteratively. When we encounter assignable causes, we are eliminating them, we are changing limits again and again, and we are trying to be more accurate about it. But there is no thing like in this. There is no such a thing in specifications. They are set values, all right? They are not the same thing. This is important. Be careful about it. And again, rational subgroups. Why are we using rational subgroups? We are using rational subgroups. They are the samples actually. The concept is itself called as rational subgroups. The concept says us we are trying to maximize between sample variability so we can detect shifts, okay? And we are trying to reduce the variability within the sample. So actually we are trying to getting, identical, observations, so we can make some comments, inference about the variability we have much more accurate. Okay, so X-bar charts monitor the between sample variability, and X-bar charts tries to detect the shifts in the process, shifts in the mean. And R charts measure the within sample variability, and it is instantaneous variability because they are mostly taken consecutively each other. And we are, estimating the standard deviation, the variability concept by our, by range values. and we are trying to reduce this variability too. Okay. So about standard deviation, we have said that we can use, sample standard deviation formulation, and we have another alternative. It was the range value, but we have used range values up to now. We didn't use standard deviation formulation because we have a reason for this. When we use sample standard deviation formulation, actually we will combine both within and between variability concepts. But we do not want this because they are different things. Because when we talk about between sample variability, we can have some shifts, and if there are some shifts, we can expect that the variability will change and it will mislead us. The variability will be much more than the actual one. So we do not want to use the sample standard deviation when we construct our control charts. Okay, that's why we are using range values, because they are more identical to each other, and their variability will tell us so much more than the sample standard formulation values. Okay. About the control chart design, we have some things to say. Let's talk about them. Control chart design requires a specification of sample size, control limit width, and sampling frequency. That's right. And there is no exact solution for that. It changes up to the process, changes up to the process owner or the experience of the quality engineers, etc. But we need to consider the cost of sampling and the cost of, OCAP. What was OCAP? This was the out of control action plan. Because when we try to eliminate assignable causes and when we take samples from the process, there is associated costs for that. So we need to consider about them. Also about the cost of, sampling and the other things, you can check chapter 10 in the textbook if you are interested about the costs and the versus different kinds of strategy about the sampling sizes and sampling frequency, etc. You can check the chapter 10 in the textbook. Okay, so for expert chart, the mean chart, we can say that the choosing a smaller sample size is consistent with the magnitude of the process shift one is trying to detect. So when we talk about the large shifts, like greater than 2 sigma in the mean, the relatively small samples are effective, like the sample size 4 or 5. But about the small shifts we are trying to detect, larger samples are suggested, like 15 to 25. Okay, and for small samples, our chart is relatively insensitive to changes in process standard deviation, right? Because when we take the range value, x max minus x minimum, when we use small samples, it doesn't change so much. But if we use large samples like 10 or 20, this range values will be changed dramatically. So that's why for larger samples, S or S square charts are better choices than the range charts. And we are gonna, in this lecture, we are gonna see the S square charts. Okay, do not worry about it. So about small shifts, the control charts are not sensitive to the small shifts. So for small shifts, we can use EVMA and sum charts. And we are gonna see these charts in chapter 9. So I'm not gonna talk about these probability limits because it's about the UK, United Kingdom. You don't need to know them, but if you are required to know them, someday you can check it. Okay, not gonna go over with the left side. Let's continue with the rest of the previous slide here. So OC curves, operating characteristics curves, and we are going to talk about operating characteristics curves in this lecture too, but also you are going to remember these curves, previous lecture we have. We can use operating characteristics curves for finding the right sample size for us. And we have some verses about the sample size and sampling frequency. We can use small sample sizes but frequent sampling. And on the other side, we can also use large sample size and less frequency sampling. There are some benefits and disadvantages for both options, but mostly in industry, if the cost of the non-conforming products is so much, we use small sample size and the frequency sampling. So also about the false alarms, when we use 3 sigma levels, false alarms, if you remember, the average run length in the null position, in control position, will be 380. But also we can use, for example, 3.5 sigma levels, for example. If we use 3.5 sigma levels, the false alarm will be lower, right? And also about another alternative. For example, we can use 2.5 sigma. Why? If we use 2.5 sigma, we are going to narrow down our control limits. And we will have more assignable causes. But if the investigation of these assignable causes is easy, it is easy to investigate these causes, we can use, narrow control limits. That's in this way we can, increase the process quality, process performance too. But if it's the case is if the investigation effort is easy, right? If we know the true value of mean and standard deviation, we can use a different formulation, but it is the same concept, but different calculations, let's say. Instead of estimating the standard deviation, we use the standard deviation value, directly. For example, in the X-bar control chart. And this is, mean plus 3. It is customary to use 3 instead of Z alpha over 2. Use 3, and this is the sample standard deviation we have. We do not estimate the standard deviation because we know what it is already. But if we do not know in real life, most of the time we do not know what is the standard deviation, so we need to estimate it. So to estimate it, we are using the relative range formulation, and we are estimating it with average range over D2, and then we are plug this term into that formulation. But this is the case for unknown sigma, but here we know the sigma value, so we directly use it. Okay, so the A here is 3 over 3 over square n. So this is also tabulated in the appendix in the book. You can use it too. About the R chart, we also use the relative range, and we know that the mean of the relative range is D2. That's why the R is the D2 multiplied with the sigma, and we know what is sigma in this case. And about the control limits, we are using the standard deviation of R, and we know the standard deviation of R by multiplying with the standard deviation itself. Okay. All right, let's continue. And in this case, we use 3, but it is not set in stone. You can use different sigma levels. It's up to you. But in the industry, the common practice is to use tree. We said that even if we do not have any other out of control point, maybe we cannot say that the process is in control, because maybe there are some non-random patterns we need to identify, and these non-random patterns occurs because of some assignable causes, so we need to eliminate these assignable causes. For example, I'm going to give some examples for non-random patterns we can have in control charts. For example, the first one is cycles. This is not random, because there is a dependence here. For example, it decreases consecutively and it increases after some point consecutively. So this is a cyclic pattern. The cause of cyclic pattern can be, for example, temperature change in the environment or operator fatigue, etc. These kind of things can be a cause for cyclic pattern. A mixture pattern can resulted from the over control, unnecessary of adjustments of the machine by the operators, and maybe there are some parallel machines doing the same job, same process, and we are taking the samples when these parallel machines, putting their output in the mainstream, and we are taking the samples out of this mainstream. Maybe this is the reason we are seeing the mixture pattern like this. Also, a shift in process level. So we see here there is a shift in the process level, and we can see that easily there is a shift here, and it can be resulted from new operator, new material, etc. The new things we can cause this kind of shift. Also, we can see some trends in the control chart, and this can be resulted from the fatigue of operators, or tools can wear out. So this can happen. This can occur. A stratification pattern, maybe it seems random, but actually this is not random, because it's just around the mean value. We do not see any value moving away from the mean value, so it does not seem random. So one of the reasons we can have stratification pattern is the lack of natural randomness. So there is no natural randomness, or it can be a wrong calculation of control limits. Maybe these are calculated wrongly, or the samples are coming from different distributions. It can happen, all right? So this is another reason for seeing stratification pattern. The final note, X-bar and R charts must be different, but if they look same, then the underlying distribution may not be normal, because if they are normal, that they must be independent from each other. Range chart and X-bar control chart must be independent from each other. If the underlying distribution is normal, they must be independent. Okay.